Awesome, let's go. Yeah, hey everyone, welcome to my talk on Apple's Lightning. First off, about me, my name is Thomas Roth. I'm a security researcher. I mainly do hardware, so it's a bit more on the hardware side compared to most of the other talks. I'm better known probably as Stacksmashing. I have like a small YouTube channel, and you can find me on Twitter at Ghidra Ninja. And yeah, as with any piece of research, I did not do this alone, and there are a lot of other people that I have to thank. And so, for example, Carlo Maragno, who is my partner in crime on the hardware side of things, Yiska and Fabian for answering all my stupid questions on the iOS kernel cache and how to load it. Then Bendikatos for a lot of, Lightning, let's say, secrets, and Jan Satan for, documenting all the SDQ and so on details in the first place. Lambda concept, as you will see, played a huge role. The CheckRain and PaleRain team, and also Linus Hense for his contributions to what you're about to see. And yeah, before we get started, let's talk a tiny bit about Lightning. So Lightning is this nice proprietary connector by Apple. It's reversible, and it's been around for like 10 years or something. And yeah, I mean, it looks pretty simple on the outside, but the devil is in the details, and it turns out that Lightning can do a lot more than just, charge your phone. And when you look at the Lightning connector itself, basically when the display is up, the contacts of the Lightning connector are on the bottom, and that's how we generally consider them when numbering and so on. And Lightning has 8 contacts. That is, unless you have that one iPad Pro that has 16 contacts in its Lightning connector, because Lightning still is only USB 2. And so to be able to actually build something that can open the hard drives, they had to change the Lightning connector and so on. But yeah, basically, normally when we talk about Lightning, we talk about 8 pins. We number them left to right, 1 to 8. And normally, Lightning is used for charging, data transfer, audio, video, if you connect your iPad to your projector and so on. But those are the boring use cases, I would say. So there are a couple of far better ones. So for example, on AliExpress, you can get these cables called DCSD or LX cables, which basically give you a serial console into the iPhone. And so you can connect this to the iPhone, and when it starts up, you get like the serial boot log of iBoot and so on, which is pretty neat. But to be honest, you also can't really do anything with it, because like on a regular phone, you just see a couple of lines and a couple of addresses, and that's it. And there's another very famous cable called the Kensi cable, which is basically the cable that Apple internally uses to debug their pre-production or EVT iPhones. And this is pretty cool because JTAG on the iPhone allows you to debug things like the boot ROM, the early bootloader, the kernel, and so on. Unfortunately, you can't really get those cables like legally. Like you can get them on eBay and so on. But I have a couple of friends who work at universities, and they're like, hey, I cannot tell my university I need $500 to buy this cable from a random dude on the internet. So yeah, but what's interesting is how all these cables work. So basically, when you open up a Lightning connector, it's not just a passive cable. There's actually multiple integrated circuits in there. And when you hook up a logic analyzer while booting up the iPhone or while plugging something into Lightning, you will see that basically the iPhone sends a ton of data over Lightning. Like this is just by plugging in an empty cable, you can see that it just keeps banging out data on 2 different channels. And when we actually plug something real in, like for example, a charging cable, you can see that just when we plug in a charging cable, a lot of stuff is happening. So for example, this here is again this weird Lightning protocol, and there's a lot of stuff going on. There's a lot of data going back and forth and so on. And we can see this all happens before power is enabled or before we even can get like USB data out. And we have to scroll through quite some data until we can actually see 2 data lines becoming active. That is our actual USB signal. So something is going on there. Some authentication or communication is happening between our cable and the iPhone. And this communication is called SDQ or ID bus. It's a pretty simple one-wire protocol. So it's just a single wire. The reason we have 2 signals is that actually the iPhone connector is not fully symmetric, and so the iPhone can detect which orientation a Lightning cable has just by on which channel it gets a response, basically. The encoding of this signal is super simple. Basically, a short low pulse followed by a longer high pulse is a 1, and the opposite is a 0. and the least significant bit is send first. This is all pretty basic and pretty simple, and basically the iPhone will send over some data. Then there's a break period where the directions change on the data line, and then the cable answers. Inside the iPhone, this is all handled by a chip called TriStar or Hydra, or probably a different secret code name on your iPhones. And TriStar is basically a multiplexer between different functionality in the iPhone. So for example, UART or serial, USB, JTAG, and so on. This list is not complete, but there's a lot you can do with TriStar or Hydra. And when you plug in a lightning cable, the phone basically just says, hey, what do you want? And then the cable says, hey, I want to speak USB, or I want to speak UART, and so on. And on the physical layer, what happens is on the connector, we have a ground pin and a power pin. And then we have these two pairs, L0P and N and L1P and N, which is basically two pairs that can be set to different configurations. And then we also have ID0 and ID1, which are the two communication lines for SDQ or ID bus. And when you connect a USB cable, it will basically talk to this TriStar chip and tell the TriStar chip, hey, I'm a USB charging cable. Please give me some USB on those pins, or please give me UART on those pins. Now this has all been known. Like I wrote an analyzer for it in 2018 or so, and Jan Satan actually documented a lot of this. And so last year, we decided, like a couple of friends, to actually implement this whole SDQ stuff on a Raspberry Pi Pico, because it's super cheap, it runs at 3.3 volts. It has this nice feature called PAO that you can use to implement these really fast protocols. Also, because of the damn chip shortage, it's actually available, and so it was really the best choice we could make. The idea was pretty simple. We hook this somehow up to the iPhone. We wait for this signal who's there, which is encoded as command 74. And then we just reply with, hey, I'm totally a USB to UART cable that is Apple internal, and I'm totally legit, and so please give me UART. And that's what the iPhone will do. And to hook up the Raspberry Pi Pico to the iPhone, we can just buy a cheap, lightning extension cable off Amazon, which is like 10 bucks or so. Cut an end off and just solder it up to a Raspberry Pi Pico. Here's the pinout. You can also find it on our GitHub. And then you end up with this contraption, which is slightly janky, but I think it's on the cool side of janky. And after a bit of coding, you actually have your own DCSD cable. And so basically you can plug in the iPhone into the Raspberry Pi Pico, and you get the serial console. So we did all of this last year and built like a full JTAG stack and so on around it. And all these cables are named by after monkeys. And so you have like the Kansi cable, the Kong cable, the chimp cable, and the bonobo cable. Luckily for us, they didn't take the coolest monkey, which is the tamarin monkey with this majestic mustache. And so we call our firmware the tamarin cable. It's been open source for a year now. And it's basically an open source DCSD JTAG adapter. And it has a couple of features which make it a bit useful for other stuff, which is it can automatically reset and DFU your iPhone. And so if you've ever tried to get an iPhone into DFU mode, it's like you grab the iPhone, you hold both buttons for exactly 8 seconds, then you have to release one, and then you have to keep holding volume down, and then eventually, after 5 tries or so, you're successfully in DFU mode, and you can actually, jailbreak your phone. With Tamarin, it's like half a second and your phone is in DFU, no touching needed. And people saw this and they started using Tamarin for automating like fuzzing and so on, which it wasn't really made for, right? Like it was really janky. It was made to debug a kernel that's running or so, and so it needed frequent replugs. But people still started, using it for automation. And so we decided, okay, let's do this and let's build some automation to make the life of these people easier. And so one of the things that we built for this is, for example, a tool to automatically jailbreak your iPhone. And so if you have a checkmatable device, instead of having to deal with like checkra1n and so on, it's literally you have your iPhone open, you hit return, and it will basically load the latest firmware onto the Tamarin cable, and then it will, do the whole exploit shebang, and then you can see that it's booting up, and your iPhone is jailbroken basically. And this takes like, I skipped the boot because we don't need to watch the Apple logo forever. But basically, this allows you to kind of build fully automated infrastructure where you run a fuzzer, and even if it crashes the kernel or resets your device, you just re-jailbreak it without touching anything. And this is really cool for automation. But this is just the first step. So the problem is if you actually want to do JTAG and want to do something more complex, let's say you want to debug a kernel crash you found early in the boot process, right? At the moment, you have to reset the device into DFU, so hold button down for 8 seconds, reset, and so on and so forth. Then you have to actually run the checkmate exploit. You have to boot into Pongo OS, which is like this pre-boot environment. You have to demote the device, and so basically enable JTAG on the device, start the kernel, start OpenOCD, attach, and so on and so forth. And this takes forever, right? Like this is really like annoying, and if you have to do it more often, it can get really frustrating. So now with what we did to make this a bit easier for fuzzing cases is basically implement a fully automatic chain to get the iPhone into a state where you can actually, debug it. And basically, we just run Tamarin debug kernel, which is a very simple script that uses all the libraries we have, and it gets into DFU mode, then it boots up Pongo OS, and then in Pongo OS itself, so Pongo OS is this basic bootstrap operating system built by the JTAGging guys, I think. And in there, it basically demotes the device and then gives us full access to the iOS kernel. And so we basically boot up the kernel and enable JTAG and can now just connect with the debugger. So this is super simple, super fast, and super easy. And this is huge because back then it took like literally minutes to actually get to the state, and then you messed something up, you forgot a step, you had to reset, you had to try over. And what we can also do with Tamarin is we can actually debug the integrated iPhone ROM. So the thing that's actually handling the boot and so on, and where checkmate is actually working. And I'm stupid or brave, depending on how you look at it, to make a hardware demo on stage. So let's give this a try. Basically, what we will do now is we will try to debug the boot ROM of the iPhone. And so I've got my trusty broken iPhone 10 here. And I will connect it up to the Tamarin cable I have laying here. So this is a bit more of an advanced version. It's a bit, we made a custom PCB for it, so it's a bit nicer to handle. I plug it in, and then hopefully, if everything goes well and the demo gods are with us, we can run Python Tamarin debug secure ROM. You can see it's lighting up, so it's doing something. The iPhone just turned off, so it's getting into DFU mode. It's now launching JTAGging, which is used to basically re-enable JTAG. And hopefully in a couple of seconds, device is demoted, entering JTAG, and we can see it's up. So we can ignore the errors, but what we can see here is that basically Tamarin connected to the iPhone. We have core 0, hardware has 6 breakpoints, 4 watch points, the other cores are turned off, so we can ignore this. And now what we can do is we can actually connect into the iPhone boot ROM and debug it. So basically I can bring up a shell. I will just run netcat, and I will say targets. And we can see we have all the cores here. We have like the debug access point, memory access point, and also ecore 0, which is one of the cores in the iPhone. And so we can say targets, iPhone.ecore 0, and now we are connected to it, and we can halt the processor. So now it's stopped. The boot ROM is just sitting there, and we can start investigating memory. And so, for example, we can look at this address here, dump 32 bytes. So let's mark this, go into Python. So you guys are all hackers, and so you probably already saw that this looks a lot like ASCII. And we can see we actually are dumping secure memory. And so we just dumped with 30 seconds of work, we just dumped parts of the iPhone boot ROM. And we can very easily do this. Takes literally 20 seconds. So that's pretty nice, I think. But like debugging, I actually had a backup video, and so I'm really glad that I don't need it. But debugging with GDB and so on is a pain, and it's really like, it's not fun to jump back and like, remember, like every time you have to go back and want to check something in the history, you have to like do this all over again. But there's Ghidra, and Ghidra just launched Ghidra 10.3. And so we've been hard at work to basically merge Tamarin and Ghidra and basically bring Tamarin support into Ghidra so that we can debug the boot ROM in Ghidra. This also works with IDA, by the way, which is really cool. So yeah. But basically what's really nice about this is with Tamarin, a monkey riding a dragon, we can basically do time travel debugging and emulation right in the boot ROM or in the early kernel stages, right in a GUI. And so basically we can just, when you open up Ghidra, the debugger, I already have the dumped ROM loaded here. I can just say, okay, I want to connect with GDB. Then I have to run a script that we built for, basically it sets up all the memory areas and so on that the boot ROM needs in Ghidra so that we get a better memory layout. And now we are connected. So basically we can see on the top right that it says, hey, I'm at address 568. And we can see in the dynamic listing that it actually fetches the memory from the device. Now we can look at the registers, we can step forward, we can do all that kind of jazz, all the usual debugging things. But what's really cool, and the main reason I wanted to implement this, is not this basic forward debugging functionality, but instead this small thing down here, which is the thread window, and more precisely this small graph. So basically what's really cool about the Ghidra debugger is that every time you take a breakpoint or every time you step, it saves the state of the program. And we can go and we can drag the mouse on there and go back in time, and we can go back through the execution history. And what's even cooler, if you're stopping somewhere, you can now adjust the register values. For example, you want to see, oh, maybe what if I change this data that I sent over? And you can emulate forward and test this right in Ghidra without having to actually test this on the hardware and reboot and do this all over again and so on. And then once you know what you want to do, you can just go back forward and then emulate forward and then decide to, for example, go back to either the actual target and modify some memory there, or continue emulating, stepping back, and so on and so forth. So this is, I think, really, really cool and something I'm pretty excited about, and it really helps with when you debug low-level stuff on the iPhone. But what do we need automation for the most? Obviously, fuzzing. If you want to fuzz some low-level stuff on the iPhone, like imagine you want to fuzz DFU, how do you fuzz it after you have a crash, right? Do you want to do the hold 8 seconds, wait, and so on over and over again? With Tamarin, we can actually fully automate this DFU fuzzing. And so basically, instead of entering DFU by pressing all these random keys, there are actually some secret, so to say, lightning commands that Bendicatus found to enter DFU automatically, as you saw. And so I wanted to build this, and so I built a basic DFU fuzzer that basically runs on the iPhone. And this is, by the way, running on a very outdated device, I will say, because I'm not so interested in the more modern ones, and they are not checkmatable and so on. But basically, this fuzzer is able to find different behaviors of the DFU that shouldn't be there. So timeouts, resets, and so on and so forth. And it's actually able to rediscover checkmate on the actual iPhone. So like with this script, you can at least discover the behavior of checkmate automatically without actually doing any reversing, which is pretty cool. And so yeah, we will release this DFU fuzzer, which only works on a modern iPhone. It will not find anything, let's say, which is why I'm comfortable with releasing it. But this is pretty cool, right? Like you can actually even build for modern iPhones, you can build fuzzers for DFU, which previously has been pretty difficult. But what about Lightning itself? And so it turns out that there are a ton of different Lightning accessories. And so, for example, you have the Apple Pencil, you have like charging cables, USB adapters, headphone adapters, and so on. And I wanted to look at how that all works and how, maybe there are differences in how they authenticate. There's this made for iPhone program, MFI, which authenticates the accessory and so on. And so I wanted to have a bit of a look at this. And so normally sniffing Lightning for me was a bit of a very janky setup. And so this is how we actually built the first successful JTAG, basically. And I wanted to have this a bit more cleaner. And so basically, I built a whole tool set around analyzing SDQ traffic. And so for that, we built the Tamarind sniffer, which basically allows you to, in real time, sniff the traffic that goes, for example, between an iPhone and your headphone adapter and so on. And it's pretty nice. It's still janky, but not as janky as having this all hooked up on breadboard. And it's fast enough to actually support like even faster adapters that do like USB 2 and so on, which is where it gets complicated. And when you plug in an accessory, it will actually fully dump you the traffic. And you can then investigate it. It will even mark you like frames that have invalid CSC values and so on. And we built a script to automatically convert this sniff into C code. And so you can basically build replay attacks for iPhone accessories with like you plug something in, you copy it over, and you can actually replay this onto the actual device, which works for a surprising amount of devices. So headphone adapters, charging cables, and so on are all replayable. And there's also some tooling for diffing multiple requests. Like sometimes it's not replayable and you want to analyze it. So we did some basic protocol bin diffing for this. Yeah, pretty simple. So all of these cables we tested are pretty small. There's like the headphone adapter is a couple of bytes, charging cable 200 bytes and so on. And I was curious what would happen if you actually just start fuzzing this, right? Like we have all the setups. The idea is pretty simple. Take recordings, mutate them, observe behaviors. Well, it turns out that the iPhone actually has some sensor that detects whether you physically replugged the damn lightning cable. And so we had to kind of build our own lightning plug that we still have to release that kind of that supports virtual re-enumeration. So basically it acts as if the cable was reconnected even though it wasn't physically. And with that we can start fuzzing. And for some accessories we actually get in the settings this nice overview on like, oh, a new accessory has been connected. And while fuzzing it looks pretty funny because it's mostly empty and we'll just keep doing this stuff and so on. But then something pretty interesting happened, which is basically this. Like my iPhone was running and it just suddenly rebooted. And so that to me indicated, hey, something went wrong. And so maybe something interesting. Now I have to be honest, I'm not a big low-level iOS guy. And so I had to start figuring out what's going on. And so, look at the log, which you normally mainly get via USB, but I don't have USB because I have Tamarind connected there. I had to figure out how to get that all over. And then it turned out that a lot of the Lightning stuff is actually handled in the kernel. And it turns out that the kernel is crashing. Oops. But luckily for Apple, unlucky for us, only on some ancient build. And so I fussed this quite a bit, and so I'm pretty comfortable with releasing this with some details, as it doesn't find a vulnerability. But it found one on older versions, and so I think Lightning is really an interesting topic to explore. And then something pretty interesting happened. I thought I would try what happens when you plug the peak of Apple industrial design, the Apple Pencil, into an iPhone. Which looks somewhat like this. And I expected this to be, I don't know what I expected to happen, right? Because like the charging adapter is like 100 bytes, like what could possibly happen? So how many bytes does it take to charge a pencil? Turns out it's 3.8 kilobytes. Yeah, exactly, what the hell? And so it turns out that there's a lot of data going over the line here. And so basically, if you look at this in a hex dump, like just dump the contents, there's even like Bluetooth pairing stuff and so on in there. And so this is something I couldn't find any public details on. So it was kind of an accidental find because who plugs his pencil into an iPhone, right? And what was really interesting is that basically at the time, this is what a normal Lightning accessory looks like. You have like short commands, short responses. It's pretty simple. However, on the Apple Pencil, there was a lot of data going on, and it was always the same commands with like addresses increasing and so on and so forth. And I couldn't find any details on this, and so I had to really dive into the kernel cache and figure a couple of things out. And it turns out that basically this is called bulk data transfers, and it's also what's used by the smart keyboard, the battery backpack, and so on. And there's zero tooling for this. Like, no, you can't find anything on this. And so I had to play with this. And the problem is the Apple Pencil is not replayable. And so I had to figure out how can I mess with the data without replaying it. And so built another tool that I call Tamarin Mitim, which obviously stands for monkey in the middle. And so basically the idea is that you have the Apple Pencil, you have Tamarin in the middle, and then the iPhone. And we can actually mess with the data that the iPhone sends. And so for example, if you have MFI and it does authentication of the accessory, we just start messing with it afterwards, right? So it looks a bit like this. If you debug it on the train to OffensiveCon, it looks like this. And so it turns out that this bulk data stuff is really complex and allows you to basically do, as the name suggests, large data transfers, and it's used for a lot of different things, and that it's also a pretty interesting target for fuzzing that is still in progress. And in the next week, hopefully, we will release some basic tools to dissect bulk data, document the basic layout, override data, and show how to mutate it and play with this. And so what I want to encourage you to do is don't just focus on the software side. The hardware interfaces are super cool, and maybe help me explore them a bit more. So thanks a lot, and yeah, see you soon.